All right, so let's start with 8.4, which is a short but intense section about adding, subtracting, and multiplying radical expressions. You'll notice that they leave dividing radical expressions off that list. Division always complicates things and deserves extra attention, so that's going to be covered in another section. And really, the main thing we need to wrap our minds around today in order to understand 8.4 is a concept that should remind you of something we already know. And what we already know is the concept of like terms. So, for example, 2x and negative 7/4 x, I'm going to make it look kind of really funky here, are like terms. So what that means is we can add or subtract them. Multiplication and division of like terms doesn't really, multiplication and division don't care if you have like terms or not. 9xy and 3x are not like terms. So no adding, no subtracting, can't go any farther. In a case like 4x minus, I'll just dredge up some of this that we had already used, plus 2x minus 6y plus 14xy. Okay, so if we have a long problem like that, an addition subtraction problem, I'll just underline the like terms. We've got a couple of x's. We've got a couple of xy's, also like terms. And then we've got this lone y term, which doesn't have anybody to combine with, so we're just going to leave that as is. So in the final part of this problem, the final version of this problem, 4x plus 2x would give us 6x. Negative 9xy plus 14xy would give us that 5xy. And then we would just have to bring the minus 6xy over. Nothing could happen to it. So a little review on like terms. Let me put one with powers here. Okay. So something where you've got matching y to the fourths, those are like terms. Okay, we are going to expand that concept and start talking about like radicals. Just an expansion on like terms where all of a sudden you've got roots involved, square roots, cube roots, and so on. Okay, so like radicals. So before I'm kind of torn whether to write the textbook definition at all, ever, because it's a little bit not wordy. The terms are a little bit mathy, but let's just look. The square root of x, let me say 4 square root of x, 3 square root of x are like radicals. Okay, let me change just one little thing. 4 square root of x and 3 fifth root of x are not, because the type of root changed. We went from a square root to a fifth root, so they're not like radicals anymore. Similarly, 4 square root of x, 3 square root of x cubed are not like radicals because we went from, even though they're both square roots, we changed out the insides of the roots. Okay, so here is what the book says. And I guess I don't need quotes there. Radicals with the same index, they call it. We'll dissect this in a minute. So they have to have the same index, and they also have to have something else called the same radicand, are like radicals. I like to put that in quotes so that we don't get tricked into thinking they're saying that they're like radicals. No, they're like radicals. So English is a fun language. Okay, the same index. We haven't talked about technical terminology for roots. The same index means they are the same type of root. So they're both square root. They're all square roots, or they're all cube roots, something like that. The same radicand. The radicand refers to what is under or inside. Okay, so I'll just write out an example here. We have 9 fifth root of x squared y cubed. Okay. Here's our index. And here, this whole thing, anything that is not the root symbol itself, but is underneath it, is our radicand. All right, so that's all the background we need to dive into the problems we're going to be working. I should say it's all the new background we need. We're going to have to rely pretty heavily on what we did in section 8.3, so one section ago. Okay. So we're just going to add or subtract here. Depending on what's indicated, depending on what the problem asks for. Okay, so we've got 3 square root of 17 plus 5 square root of 17. And those are like radicals. They are both square roots. They are both square roots of 17. So all we do is add the 3 and the 5 to get 8. And keep that square root of 17. It is very much like, so I'm going to say it's very similar to if we had 3x plus 5x, we added it together and got 8x. So the radicals, the root parts of it, just right along. We don't change them at all. All right, here we've got 7 out front of a cube root of 5z minus 12 out front of a cube root of 5z. So the cube roots match, the 5z's match. 12 minus 7, negative 5. Cube root of 5z. Okay. And then finally, for our first practice problem, we get this. Notice that we have a square root of cube root. Square root of 2, cube root of 2. That's a problem. So let me see how they phrase it when this happens. It's just you can't simplify it. Keep wanting to put a y in there. Can't be simplified. They're not like terms, not like radicals, so you can't do anything. Okay, so all is well and good when they just are very upfront about whether or not you can add or subtract these things. It gets a little bit more interesting, we'll say, when you might have some hidden like radicals. So for example, at first glance, square root of 24 and the square root of 54 can't be added together on the surface of things because they're not like radicals. But what we're going to discover is that the square root of 24 and the square root of 54, neither one of those quantities are simplified down to their lowest form. And the hidden message in all of this is that we need to be dealing with simplified roots before we can ever get anywhere with the question of whether to simplify them or not. Okay, so here's what I mean. 24 is 4 times 6. 54 is 9 times 6, and I'm breaking these apart strategically because I'm looking for perfect squares that are a factor of either one. So as a brief review, our handy list of perfect squares that appears in section 8.3 in the book as well. If you have 2 squared, it's 4. If you have 3 squared, it's 9. If you have 4 squared, it's 16. 5 squared, it's 25, and so on. So I found a 4 hiding inside the first one of these, and I found a 9 hiding inside the second one. And just as a word to the wise, if there's ever 2 square roots or 2 perfect squares that would divide into one of these numbers, you pick the bigger to emphasize. Okay, so square root of 4 times square root of 6, square root of 9 times square root of 6, and the square root of 4 is 2. The square root of 9 is another 3 here. So what we get, hiding under all of that extra stuff, we're actually a pair of like radicals. So 2 plus 9 is 11. Carry over that square root of 6 and you're good to go. So you don't want to jump too quickly to the conclusion that you can't add or subtract a couple of radicals together. You want to simplify them as far as you can get them and then figure out so cube roots all over the place here. All right, so my handy list of perfect cubes. Okay, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, so on. So I can see right away 24 is 8 times 3. And let me go ahead and just start doing this. You can just break it apart right away when you recognize that 8 and that 3. Now, I don't think I went up far enough here. No, I did. I'm good. Never mind. Okay, 4 here. And then 81 is it 27 times 3? Yeah. So I can break that apart. And then the cube root of 3 here at the end is just going to hang out there for a while and wait for everybody else to catch up. So the cube root of 8 is 2. The cube root of 27 is 3. Notice that all the radicals, all the roots themselves are very nicely falling into form here as like radicals. So we will be able to get somewhere with the adding and the subtracting as soon as I kind of simplify what's going on out front of that middle root. All right, so 2 minus 12 plus 1, essentially, is negative 10 plus 1, negative 9, and then the cube roots of 3 are just along for the ride, just as though they were x's or y's or some other variable. All right, part C. So I've got a square root of 75x. So now we're starting to include variables under our roots. So that's going to make everything a little bit more exciting. Okay. So the perfect squares, if you need to dash back up and check that list out again. 75 is 25 times 3. And what I'm going to do, the 25 is the perfect square part. That's the part we really care about. I'm going to leave the leftover 3 in here with the x because we know the x has to stay in there forever. Same with 27. 27 is 9 times 3. The 9 is the interesting part. So the 3 will stay under there with the x. And then 12 becomes 4 times 3. 4 is the interesting part. 3x. So we're strategically breaking these apart. Again, looking for the largest perfect square that could be a factor of each of these numbers. All right, so the square root of 25 is 5. Got an extra 3 here when I square root that 9. Okay. And everything wraps up pretty smoothly from here on out. Okay, 5 minus 9, that's -4, plus 2, -2, and the root is just along for the ride. Addition and subtraction do not change the root. Now, multiplication and division would mess with the root big time, but addition and subtraction do not. All right, square root of 40 plus cube root of 40. Now this is interesting because you can tell right off the bat, we don't have any hope of adding together a square root and a cube root. They're just, you can't ever get anywhere with that. However, the problem is not going to be considered simplified. In other words, the problem is not going to be considered correct, 100% correct, unless we simplify. So simplify even though we know for 100% certainty that there will not be any like radicals. Kind of like with fractions, you always reduce the fraction, you always simplify the root. So let's see. 40, 4 times 10 would be a good way to break that apart. And here, this 40, 8 times 5, I can find that cube root of 8 hiding in there. Okay, so I get 2 square roots of 10 plus 2 cube roots of 5. It doesn't feel any better. We couldn't bring those things together, but that is a correct answer. It's like as though all the fractions have been reduced. So just know that your simplification efforts don't always allow you to then add or subtract anything together. It's not a guarantee, unfortunately. Okay, so cube root 81x to the 4th plus a cube root of 3x to the 4th. Now here, remembering what we talked about in the last section, section 8.3, you look at what type of root you're dealing with. You're dealing with cube roots, and you look at the power of any variables, and notice that 3 will divide into 4. Look, Matthew, I think the bagel person came to look out the window. 3 will divide into 4, not evenly, but 3 is smaller than 4. So there is hope of us being able to simplify this further. So I'm going to be extra careful with my efforts here. Got cube root of 81, cube root of x to the 4th. We've got cube root of 3, cube root of x to the 4th. Okay. Now, the 81 needs a little bit of work. I think we handled a cube root of 81 a minute ago. That is, we'll get it in just a minute. Let me finish this problem and then we will get it. Okay, so 27 times 3 And then 4, remember I'm trying to use the product rule to break this apart. And when I'm using the product rule for exponents, I'm thinking about the addition of the exponents. What adds to be 4? 3 plus 1 would be great because 3 is divisible by the type of root it is. So I've got like that, because if I rewound that process, 3 plus 1 would give me 4. Okay. So this stage of the process, when you're learning and you're just being extra cautious and putting in all these roots, it can look so messy. But it cleans up pretty nicely. So cube root of 27 is 3. Then we've got a cube root of 3 that's stuck as is. Then we've got, remember that the step that I put in is to take advantage of turning roots into powers if you would like. Now you know the 3 and the third are just going to cancel to a 1. So if you want to think about doing that and skipping this step, I'm just cautious of skipping too many things while we're learning. And cube root of x first. All right, so 3, cube root of 3, x to the first, cube root of x to the first, which I can just now call the cube root of x, cube root of 3, x, cube root of x. And so I'm going to clean this up. The parts that are not under a root are going to come out front. The parts that are stuck under a root are going to remain at the back. Similarly here, this x can come out to the front. And then the cube root will kind of absorb the 3 and the x. And lo and behold, all that hard work. Now, we have to be extra careful here. We have like radicals. That's good news. That usually signals that we could go ahead and add these things together, but not always. Notice the presence of an x out front. We now have to make sure that the x's match too. So in a broader sense, the like radicals have to be part of like terms. So we have if we had like an x squared and then like radicals, we would still not be able to add it together. So it just brings a level of complication that we really probably didn't want in our lives. 3x plus 1x would be 4x, and now we've got this extra stuff just sort of tagging along there. So that last example, very crucial to understanding this concept. Okay, let me pause. I shall return shortly, hopefully. Okay, so just got a couple of practice problems left, but as you can probably tell from the last one, there's a lot in each one of these problems. Okay, so still being given addition and subtraction problems, but now they're starting to include fractions. I'm doubly sure I actually restarted the recording there. So now we're going to have to think, you know, the like term idea from the previous problem is going to start to include common denominators, lucky us. So the only square root I can break down is the 28. And if I refer to my handy list of perfect squares, it looks like 4 times 7 is the way to go. So I'll handle that first. I'll worry about getting like radicals, or simplifying radicals, I should say. I never am guaranteed like radicals before I worry about common denominators. So the square root of 4 becomes a 2. And this is as simplified as I can go in terms of roots. Now I have to start worrying about the fact that one of my fractions has a 3 underneath and the other has a 4. That means they get a common denominator if they both had a 12. So let me fix, see what's missing. I need a 4 here, and I'm going to multiply that 4 to the 2. in that first fraction. And then it looks like I need a 3, and I'm going to stick the 3 right out front here. I like to always stick my numbers out front of the roots so that they're not in danger of being sort of sucked into the roots. If we're not careful as we walk through step after step after step, maybe we pick up speed in the problem. Before you know it, if I had multiplied that 3 to the back, that 3 could have slid under there with the 7. It's easy, easy, easy to do that. Okay, so I've got 8 square roots of 7 over 12. Just stick it on the napkin. Minus 3 square roots of 7 over 12. And now I'm good to go. I happen to be lucky enough to get like radicals. And now common denominators give me like terms. So 8 minus 3 is going to give me a 5. And then everything else stays the same. Like that. Okay, part B. Mercifully, this is the end of this practice problem. Before they get too carried away with fractions, we're going to be done. Okay, now I can see those cube roots of 6y. I can see like radicals in my future. In order to unlock that, though, I need to use the quotient rule type of an idea from the previous section. And this could be the backwards quotient rule. Now I can't remember which way was forwards and which way was backwards, but this is honestly the first way you learned the quotient rule because I gave you that little preview a couple of sections ago before the book knew what we were up to, before the book was ready to teach us that. Okay. And 64, if you check your handy list of perfect cubes, 64 is a perfect cube. It's 4 to the 3rd power. So we can write this now as cube root of 6y over 4 plus 3 times the cube root of 6y. Now what this means right now, in order to be able to add these together, I do have a fraction. It's just over an invisible 1. If I want to be able to get a 4 under there, I have to go through the procedure for creating common denominators like that, multiply by what's missing, in other words. All right, and then maybe it's time to reveal yet another invisible 1. Add those together, 1 plus 12 gives you 13 over 4 next to the cube root of 6y. All right, now that brings us to the end of adding and subtracting. The only thing that we need to do to complete this section is start talking about multiplying these things. And in a way, that's going to change the game entirely. So let's very carefully wade into this practice problem because there's not a lot of, well, there's no definitions or anything that I need to put up on the board. I just need to remind us about concepts that are going to crop up in these problems anyway. For example, the distributive property is going to crop up right here. Okay, so being very careful with this is checking to see how they handle it. The square root of 5 will multiply to that 2. And then the square root of 5 will multiply to that 15. Now, the way that it does this, there are options. Maybe some are not better than others. But I have a little bit of a preference, and I'll show you how we're going to do this. So when I multiply the square root of 5 by 2, this is legal, but like I mentioned a minute ago, it's safer to keep that 2 out front. Okay, so we're going to do that. And then if you want to just keep with that theme, the square root of 15 times the square root of 5, we can go ahead and do that as well. Okay, now here's where it gets interesting, because you could, with 100% permission from algebra, you could go ahead and say, well, let me combine my 15 times my 5. And what's that? 15, 30, 40, 30, 60, 75. You could go ahead and do that. And then you would think about, well, 75 is 25 times 3. That's not a super bad idea in this particular problem because the numbers never get gigantic. But, you know, we're dealing with 15 and a 5, and then we multiply and we get 75. Numbers could get large in the future. So what I'm going to choose to do instead is break apart that 15. So there's no way that a perfect square can come out of there. 15 really only breaks apart as like 5 times 3, or I'm going to strategically call it 3 times 5 so that my other 5 is right there next to the 5 I just created. Okay. 2 square roots of 5 plus 3, square root of 3. A couple of ways you can look at this. The square root of 5 times the square root of 5 is just 5, is perhaps the easiest way. Or if you want to bring them together and kind of think about, this is now the square root of 5 squared. And we had a mechanism for handling that in a previous section. A couple of different mechanisms for handling that. Either way, eventually you're going to unlock that 5. Okay, so 2 square roots of 5 plus 5 square roots of 3, and there we're stuck because we don't have like radicals, so we can't even ask ourselves about like terms. Right, so that was a little bit of practice with the distributive property. Not too bad, but a lot of thinking involved. All right, part B, if we could handle a simple distributive property, let's handle a 2-part distributive property, sometimes known as foiling. All right, so let me very carefully take my square root of 2 and distribute it through, and then its turn will be over, and we will focus on the square root of 5 getting to do the same thing, and it's technically a minus square root of 5. We're going to be bringing that negative along with it. Okay, so we get the square root of 2. I'm trying to think if there's an easier way to do this. Let's see if this works. I apologize if this throws anybody off. Square root of 2 times the square root of 6 plus the square root of 2 times 2. Now, the square root of 2 times 2, again, I prefer to call that 2 times the square root of 2 for safety's sake. Okay. Mama. Thank you, Matthew. Are you finished? Okay, now I have my negative. Okay, that's fine. I'm almost done here, baby. We're on my last few problems. Negative square root of 5 times the square root of 6 minus the square root of 5 times 2. And again, this gets weird. To avoid doing this, sticking the 2 at the end, what I would have to do is stick the 2 right there. And I do. Go bring me the little spray from the bathroom. So that's what the distribution step looks like. Ugly, 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 ugly. Okay, so again, I am totally permitted to combine the 2 and the 6 as a 12, and then think about breaking apart the 12, but I'm not going to do that. Instead, I am going to break that 6 apart into 2 times 3. Okay, so I've got that. Oh, okay, good. Good. That's right, because we had it out here earlier, didn't we? Okay, so now the 5 and the 6 under the square roots, if you think about what could happen here, what benefit there is to us in choosing one method over another, 6 can only be broken apart as 3 times 2, or 6 times 1, but you know, that's not even worth mentioning. We will not find any square roots of 5 in there, anything matching. So honestly, at this point, you might as well bring the 5 and the 6 together. So let me go ahead. 5 times 6 is 30. Nothing can come out of there because we weren't able to find any matching square roots hiding in either one of those guys. Okay, so here, a couple of square roots of 2 come together as a whole number 2. And believe it or not, all that hard work, which I'm pretty sure we did correctly, we do not unlock even one pair of like radicals to reward ourselves with. So there it is, feeling uglier than it was when we started. Okay, we have got a load and a half of these problems to do. I'm going to square to z. Okay, so same idea here. I'm just going to grab my orange and my green. I've got a multiplication here. I just have a few more problems. If you go find some clothes, we can get you ready as soon as I'm finished here in a minute. Okay, so let me continue with the color coding. And this is going to be even more interesting than before. I'm going to spread this out. So the 3 square root of z multiplies across. And because everything's so complicated over here, I'm not going to worry about arranging anything just yet. Plus 3 times, since this is just a 3 and it doesn't have a root attached, I'll keep tucking it in front of my terms. Whereas here, when I had a number and a root times a number and a root, I didn't try to arrange anything to my benefit just yet. I just kind of stuck it there. Okay, now I've got minus 4 and minus 4. Let's see how this is going to work if I've spaced this correctly. Okay, times 2 square roots of z minus 4 times 3. Okay, so with extreme caution here, 3 times 2 is 6. What is that?
A posture.
I see it. Are there any shorts or pants to go with it? I think you grabbed 2. I think you grabbed 2 shirts, so you're going to need some pants. Square root of z times the square root of z is just z. Sorry, I got distracted by something I thought I had read. Plus 9 square root of z minus 8 square root of z minus 12. Yay. Okay, so our hard work pays off a little bit here. 9 minus 8 is 1 square root of z, or just the square root of z, and then minus 12. And what I was looking at, I'm going to zoom up to the top of, they stick this somewhere, I think in the middle. For some reason, I thought they covered it in the instructions to the practice problem, and they didn't to one of the practice problems. So assume all variables are positive, real, or represent, they say, positive real numbers. It's this little thing we have to have anytime we start taking square roots or fourth roots, any even numbered roots. Specifically, no absolute value bars needed. Okay, good job. You can try to put that on, or you can wait about 5 minutes and then I'll help you. Okay, so I'm just going to put that. I know that's not something that we typically think about, but it's something the book and I are duty bound to just kind of state. Okay. Okay, so that was part C. Now we get part D. Square root of 6 minus 3, quantity, that whole quantity squared. So I'm just going to immediately break this apart. Okay, not even going to attempt to square it out in the previous form. Okay, so very carefully here. Do that. Maybe we can step away from the color coding a little bit. So square root of 6 times square root of 6. Square root of 6 minus 3. So I'm going to call that minus 3 square root of 6. I get another minus 3 square root of 6 because this is the same term twice. And then I get minus 3 times minus 3. At some point when this starts feeling comfortable, the temptation to do some of this in your head will start taking place, and that's, in a way, go for it. You know, as you multiply the square root of 6 times the square root of 6, you could just go down to write a 6 if you feel comfortable enough. You'll know that it's the wrong time. Sorry, I was distracted thinking about a previous problem. My mind is always half in another place. You'll know that you're too early to do. No, not quite. 5 more minutes. You'll know that maybe you jumped the gun and started doing things in your head too early if you're getting the answers wrong. You can always backtrack, put in more steps. All right, so 2 more of these wonderful, enjoyable problems. Okay, now here, before diving into the foiling, even though there's nothing wrong with diving into the foiling, I would just ask you to notice that you've got an A plus B, A minus B situation, which turns into an A squared minus B squared. So just notice that it's one of those formulas. Since we had to put in the effort to memorize it, okay, you can put them in your jar if you want. Yeah, I'll look at it in a minute. Okay, so what we get is something squared minus something else squared. Like that. Okay, now if I am squaring away a square root, that releases the insides. And then, of course, if I'm squaring a 3, I just get a 9. So maybe that memorized formula speeds up the process of foiling a little bit. Okay, and then finally, now here is something where there is a memorized formula. We did not choose to emphasize that. Kind of like there's really a memorized formula for this as well. Yeah, I told you about 5 minutes. Be careful with the cord. So we've got to expand it. I still stand by my decision to not have us memorize this formula. It's just kind of a waste of time. So very carefully here. not skipping any steps. Just follow the direction of my arrows there as I slide these things up next to each other. Okay, so I have matching square roots. That releases the inner quantity. I have like radicals that I can add together. And then towards the bitter end here, I've got a 2 and a 9 that are like terms. So in whatever order you feel right about it, I've got x plus 6 square root of x plus 2 plus 11. So there it is. That is section 8.4. Only 4 practice problems. They're just pretty involved. Sets the stage for 8.5, which is even more involved. So kind of hold on to your hats. We're at a kind of a tough section, kind of a tough part of the course here. Honestly, it's been tough since what, chapter 6? So, or maybe I should say extra tough. But it's all doable. Just make sure you practice these things a lot. I would try to rework every single problem that you've seen me work on the screen before you attempt any textbook problems, if it's a section where you're really just feeling shaky. Because you've got my answers, you've got my work, you've got the books examples you could work through as well. So working through things where you've got the solution laid out for you is great. Kind of training yourself to not look at the solution, or maybe only to look at it one line at a time as you go through. But that can help you build some confidence instead of diving right into the odd numbered problems that the book has, because they, at first glance, a lot of these odd number problems might look nothing like what we did in class, because there's just so much room for creativity on the part of the book. So let me get my recording saving.